Can you guys hear me at the back? Okay, perfect. While people are walking in, we'll wait for a couple of minutes. Meanwhile, can somebody tell me how they felt about yesterday's lecture, how helpful it was, how difficult it was, how easy it was? Anyone? Some feedback would be really nice because it's a feedback system. You tell me something and then I'll try to maybe make it better. Come on, you're a group of master students. You can't be that shy. Yes, please, go ahead. Okay. Okay. So there is, of course, some mathematics involved in machine learning, but the thing is, you wouldn't actually need that math when you're implementing a machine learning system. It would be taken care of for you. Why we actually need it is because, let's say, you train a machine learning system, you get some output. More often than not, that output would not be what you want. And then you would have to change something in your machine learning system to make it work. So it's good to understand the math of it in order for you to be actually able to know the right thing to change. No, you don't have to teach it. The program knows it. When you would be using like a standard package, let's say PyTorch or TensorFlow, you would never have to write the equation of gradients or anything. It would be taken care of for you. But it's good to know it's not doing some magic. It's doing some simple optimization. And if you know what that optimization is, it might reduce a lot of work for you. Because let's say you don't know how machine learning algorithm is doing something, you would have to try random things to make it work. So let's say you would say, okay, let's decrease the number of units, let's increase the number of units, let's increase a layer, let's increase the number of parameters and see what happens. And then that's a very painful process. But if you know some theory of why it's doing what it's doing, then you can make some smart decisions. So that's actually the idea. Yes, you have something to say. Yes, please go ahead again. I think you had some comment. No, we would primarily stick to the theory of it, but there would be some examples where I would show how it works. Okay, but just to tell you, the coding part, machine learning is not terribly difficult. It's very easy. Like, you can actually look at any good book on PyTorch and TensorFlow and you can actually, the theory part is something which you would probably might not find exceptional resources on. The practical part is quite simple. Any other suggestions, any other comments? Which department are you from, by the way?
I'm from
Marine Sciences, okay. Any other comments, questions, things that we can improve or something that you want to see in the coming lectures? Okay, so what we're going to do is, I actually need a bit of help from you guys in trying to set up the stage for today's work. So let's say I have some data, xi's and yi's. Xi are the input and yi are the output for the system that I want to learn. And let's say my hypothesis function let's make it 0. So I'm using j for power and I for sample. So you guys have to help me set up a cost function for a linear regression problem and then tell me how to solve it. Okay? So I have a hypothesis function which has n plus 1 n unknowns, and I have n plus 1 bases, polynomial bases, and I want to find the best values of theta i's, the j's, which would fit my data. So what do I do? How will I start in order to solve this problem? Anyone? I need a volunteer. Okay, that's awfully quiet. So yeah, I'm just going to revise what we did yesterday. So basically what we did was we said that we start with the assumption that yi is equal to h theta of xi plus some noise. Okay, and we would write this for all the data points, all of the I equal to 1 till m data points that we have. Okay, so this would become y1, y2 up till ym is equal to, the unknowns are theta 0, theta 1 up till theta n plus some noise, some error, e1, e2 up till em. Okay, so we have a matrix missing here. Can someone tell me what this matrix is? Sorry? Okay, it's a matrix of polynomial bases. Okay, and basically what we have is x power 0 here, x power 1 here, x power 2 here. In order to keep the notation consistent, I'm just going to put the powers in the brackets, in the parentheses, so that you know that it's different from the sample number. Okay, up till x power n. Okay, so this is a vectorized representation of our equations, the system of equation. Now what do we want to minimize? We want to minimize the error in this formulation. So basically we write our cost function and minimize it with respect to theta, where theta is the vector of all parameters, E transpose E. Okay, so far so good. Everyone is clear as to what we are doing? So basically I'm taking the square of each component of this error or discrepancy between my hypothesis and the true result. I'm adding them up and I'm minimizing it. Okay. If it's not clear, you can just raise your hand and say that doesn't make sense, and I will explain it. If you guys are quiet, I would assume that it's probably clear to you guys. Okay, is it clear though? Okay, so to minimize this, to actually find the value of theta which works, you would say minimize theta and just put the value of E transpose here. So E transpose is, let's call this Y, let's call this A, and let's call this Z. Then we can write this as Y minus AZ transpose, whole transpose, Y minus AZ. Okay? This is something that we went through yesterday, and we are minimizing this with respect to theta, which in this case is the vector Z in my notation. Okay? and then we minimized it and we found that the optimum Z is A transpose A inverse A transpose Y. Okay, is it clear to everyone though? Okay, that's linear least squares, one of the simplest form of linear regression, and we can find actually the optimum weight of polynomial bases to fit some data that we have observed. Okay, so that was just a review of what we did yesterday. By the way, were there some people who were absent yesterday? Because the class looks much smaller than, much bigger than it was yesterday. So if you were absent, just raise your hand. And okay, so you're here for the first time. Okay. Anyone else who wasn't here yesterday and is here today? Okay. Okay. So this is an outline for today, what we are trying to do today. Once again, please ask questions. I don't mind questions. And any question is a good question. Don't think that a question can be too simple or not smart enough. Just ask the question, and then we will try to figure out a good answer. It's answers which can be slightly stupid. Questions are fine. So I am at risk of sounding not very smart. You guys are fine. Ask questions if and when you have questions. Okay? So this is the outline for today. We will do a quick review of some optimization techniques, okay, that we would need to find optimum solutions for in our machine learning algorithms. And we would have a look at gradient descent algorithm. If it sounds quite fancy, let's not worry about it. When the time comes, I'll explain it. It's quite simple. There is nothing too fancy about it. By the way, how many of you know about gradient descent and stochastic gradient descent? Just quick, okay. So at least two guys. Okay, we would have a look at stochastic gradient descent, and if time permits, we would just look at a bias variance trade-off and see how it fits in our machine learning framework. Okay. So let's start with having. I'm just going to introduce a bit of motivation as to why do we need optimization tools. Okay, so far what we have studied is linear regression, where the weights that we were trying to learn, our cost function or our hypothesis was linear in that weights, and it was fairly easy to solve that system of equation. But our hypothesis function does not have to be linear in the weights that we are trying to find. So I'll just give you an example. Let's say I have a hypothesis function which depends on m and b. It's taking the same two variable that we had in the previous example, the simple linear regression example. But now my loss function is, or my hypothesis function, sorry, is, let's say, mxi plus b, where this is, let's say, 1 plus 1 exponent minus z. So this is a sigmoid function. I'm just giving you an example of a nonlinear hypothesis function. Okay. So this is nonlinear. This is, our hypothesis function is not linear in the unknowns anymore. Okay. So in order to solve cost functions which depend on hypothesis like this, we need to have some optimization tools to find the right values of the weights that we are trying to find. So that's why we need to have a look at optimization tools. Okay, let's just quickly go through it. I'll just see where you guys are, how much of it you already know, and then we will set up a pace and go through all these topics. Okay. So we'll start with the simplest thing first. So Taylor series. How many of you are familiar with Taylor series? Just raise your hands, please. Yeah, let's say like maybe 25%. Okay. So Taylor series expansion for a function x around a point x star is f of x star plus delta x, and then you just write it like this. Okay. I'm not going to explain it a lot, just something that you can actually memorize. So it's the value of the function at x star, the derivative plus the derivative of the function at x star times delta x, plus the second derivative of the function at x star delta x square, and so on. You can add all these terms. And Taylor series is actually quite helpful in understanding us and allowing us understanding of optimization techniques and the tools that we need. So for example, I'm just going to give you one simple example. Let's say if I take the Taylor series in 1D, and I'm writing the first two terms of the Taylor series expansion. So that would be f of x star plus the derivative of f of x star times delta x. Okay. So yesterday we saw some things. We said that for a point or for a function to have a minima or a maxima at a point, the derivative of that function has to be 0 at that point. Okay. And my claim is that you can actually see it quite clearly here. Okay. So let's say x star is a maxima or a minima. Okay. So if you give me any value of the derivative of f at x star other than 0, I can show that it's not a minima or a maxima. Okay. So let's look at example. So what do you guys like more, a maxima or a minima? Just say one of these. Minima. Okay. Let's assume that f of x has a minima at x star. Okay. So we can have, it's in 1D, we can have three cases. So the three cases are the derivative of function at x star is equal to 0. We don't need to look at it because we claim that this would mean that it's either maxima or a minima. But in this case, we have chosen that this is a minima. So let's look at if f dash x is greater than 0. Okay. Then I can just choose a value of delta x which is positive, and we can show that there is a point around x star. Actually, it should be the other way around. I can choose a delta x less than 0, and we can show that there is a point in the neighborhood of x star which is less than, for which the value of the function is less than f of x star. So it's not a minima. Okay? Does it make sense? So let's say that I'm just going to write this. So f of x star plus delta x minus x is equal to okay, and for f of x star to be minima, f of x star plus delta x has to be greater than f of x star, right, for all delta x, otherwise it would not be a minima, right? So x star is a minima if for small enough delta x this value is bigger than this. Okay, just simple, because this is a minima, so this definitely is less than any, for small delta x, any neighborhood around this point. So I'll draw a figure to show you. So let's say this is an x star, and this is f of x star. Then for small delta x, any small delta x, all these points have to be greater than maybe some other delta x. All these points have to be greater than f of x star. Otherwise it would not be a minima if you have a point which is less than that. And we can see that any other value of derivative, either less than or greater than 0, you can find a delta x which will break that condition. So that's why the first derivative of a function has to be 0 in order for it to have a maxima or a minima or a point of inflection. Does it make sense? Okay. You can make the same argument about the second derivative. So So I have assumed that the first, let's assume it's, again we will take that it's a minima. We have already established that the derivative has to be 0. So now we can just write the approximation of the function as this: f of x star plus delta x is equal to f of x star plus the second derivative of f at x star delta x square divided by 2. Okay. Now delta x square is always positive, right? Because it's square of a quantity. Okay. Now in order for there to be a maxima at x star, this quantity has to be greater than 0 as well, right? Does it make sense? So the second derivative is greater than 0, we say that there is a minima, right? Because delta x square, this is square of a quantity, it's always positive. If this is positive as well, then f of x plus delta x would be greater than f of x star. So you would have inevitably a minima. So these properties, if let's say sometime you're lost and you don't know what exactly is a minima or a maxima, just write a Taylor series expansion, first two terms, and you can actually see all of these quite clearly. But it's always actually quite helpful to see that this is not some random thing that we have come up. There is actually a reason why we say that the derivative is equal to 0, second derivative is positive, then it's a minima. If it's negative and the derivative is equal to 0, then it's a maxima, and so on. But it's a good, and again, of course, we can extend it into multiple dimensions. So if you look at it, in place of first derivative, we will get the gradient vector, okay? And in place of the second derivative, we would get the Hessian matrix, okay? So does everybody know what's gradient, how a gradient is defined for a function? If you don't, please raise your hand. Okay. Okay. So I'm just going to write it just in case. So let's say you have a function of two variables, f, then the gradient of the function f at x star would be the partial derivative of f. X star, by the way, is a vector. In fact, let me just write it x star y star so that there is no confusion. The partial derivative of f with respect to x star and the partial derivative of f with respect to y star stacked in a vector. So that's the gradient of the function. How much the function changes in the direction of x, how much the function changes in the direction of y, and if there are more independent variables, all those else as well. What is a Hessian matrix then? Anybody wants to guess? So it's a matrix of second derivatives. So Hessian matrix, which here we have written like this, is the second derivative with respect to x square, the second derivative with respect to x and y, the second derivative with respect to x and y, and the second derivative with respect to y. Okay. So of course it's fairly intuitive that this would become a matrix, because you have to change, you have to take the second derivative with respect to each variable. So that's the Hessian matrix for this system of two variables. By the way, what is the equivalent of the condition for a minima in 2D to what we saw in 1D? Anybody wants to take a guess? If you want to find a minima in 2D, what would we check? Gradient goes 0? Exactly, yeah. So gradient is 0 and the Hessian matrix is positive definite. Okay, what does positive definite mean? I'm just going to write the simplest definition of positive definiteness, which is that if H is a matrix, then X transpose X is greater than 0 for all X. That's it. You don't need to look at anything else. And we already saw why we need this kind of property, that for all delta X, a quantity should be greater than 0, because in order for it to be minima, we have to ensure that in any neighborhood around this point, the value of the function should increase for it to be a minima, otherwise it would not be a minima. So this is like just some simple tricks that you can use to get used to the idea of how these optimizations, most of it would just depend on the first and second derivatives, gradients and Hessian, so you don't need to go into quite a lot of complexity. So I'm going to make a proposition here, and the proposition here is that let's say I have a hypothesis function which is nonlinear. Okay, I found the gradient of my cost function and I have a nonlinear equation that I have to solve. So basically let me just say that my cost function, which depends on some variable m and b, okay, I took its, let's make it just one variable so that it's easy. I took its derivative with respect to m and I got, let's say, some nonlinear equation, m cubed plus 4m square minus 3m plus 1. Okay, and I have to set it equal to 0 in order to find the minima or the critical points. It can't be maxima in this case because we don't know if J is convex or not yet. So any ideas how we would do it? How would we find the zeros of this equation? It's a nonlinear equation. More likely than not, we would use some iterative scheme like Newton method to actually find its minima. And again, it's just a fancy technique of Taylor series. We just use some magic of Taylor series to actually find its minima. So basically what we say is that, let's say, in this case I'm using the notation m, so I would just write f of m. Let's say you have a function f of m and you want to find its zeros. You want to set it equal to 0 and find where it's equal to 0. So we can say that for a point, you can write the Taylor series expansion like this. Right? This is the first order Taylor series expansion. And rather than setting the function, rather than setting this f of m equal to 0, we say that let's solve this. Let's put this equal to 0 and see which delta m would give us a 0 for this function. So it's fairly easy to solve. For delta m, you can say that this is negative f of m divided by the derivative of m. And you repeat this process iteratively. So let me show you what's happening in a figure. So let's say I have some nonlinear function. Okay, I start with some initialization for my m. I call it m0. I write the first order Taylor series approximation of my function at this point. So it would be this. Everybody agrees that this is the first order Taylor series approximation of my function, right? So basically the first order Taylor series approximation depends on the value of the function and the gradient of the function. So the value of the function, of course, it means that you would be at that point, you have to pass through that point. So I am passing through f of m, and it's a linear function because it's a function of delta m only, not delta m square and everything. So it's a line. As you change delta m, you will get a line with a slope f, the derivative of f with respect to m. So it essentially has to be a tangent to that function. Okay, does it make sense? Okay, and then, then I have set it equal to 0, so I'm actually looking where this first order approximation is intersecting the x-axis, and it's doing it here. Then I take this as the value of m at first iteration and repeat the process. And if you repeat it, you will eventually find a point which is the minima. This is Newton method. This is a summary of Newton method. Okay? But what I want to convey to you that it's basically an iterative scheme. It's not as simple as taking a matrix and inverting it. Okay? So the technique that we saw up till now, we had a matrix for a linear regression system. we invert it, and we get a solution. Again, that too is not always possible. So let's say you have a matrix which is a size, let's say 10,000 by 10,000. So how many operations would we need to invert that matrix? So let's say you have a matrix A which is 10,000 by 10,000. How many operations do we need to invert a matrix like this? Anybody wants to guess? 1 million? 100 million? Okay, these are good guesses. But it's for a matrix of size n by n, it takes of the order of n cube operation to invert it. Okay, so that would be this many operations. That's fairly large. I don't know. It's a trillion. I don't know how many operations are these. Okay, and a standard laptop can do like 10 to the power 6 to 10 to the power 7 operations per second. So we would remove these. Let's say even these. So that's now 100,000 seconds to find the inverse of that matrix. And 100,000 seconds, I don't know about you, but I wouldn't want to wait for 100,000 seconds to get the inverse of a matrix. So the easiest solution in terms of theory might not always be possible to implement. In terms of theory, like doing on paper, might not always be possible to implement. Okay, 100,000 seconds is I don't know, it's 3600, so 3,000, it's around 33 hours, so 1.5 days. I wouldn't wait 1.5 days. Okay, so in order to avoid these problems like trying to find inverse of matrices which are terribly huge, we have some techniques where you can find actually the solution of a problem quite easily. Okay, and before writing anything on the board, I'm just going to give you a practical example that I really like and works in most of the lecture halls on campuses. So let's assume that we are in a 2D plane and the height above the ground is a function. It represents the value of the function f of x and y. So my function value is 0 because I'm standing at a height 0, and as you go one step up, your function value would be that step. So for you guys in the second row, your f and x and y is 2. For you it's 4, and I think for the last row it's 15. Okay? Now what I suggest is that if I am anywhere in this plane, I can find a minima by just looking at two properties locally. In fact, just looking at one property locally. Let's say I'm here. Okay? I would just look at local gradient. What is local gradient? Local gradient is a step in the neighborhood, and I take the step which gives me the least value of all the steps that I can take. So I close my eyes, hopefully I don't fall down, but I'll just take a step in a direction which takes me in the maximum descent, which gives me the largest decrease in my value. So my value right now is 1, 2, 3, 4, 5, 6, and I would see which step gives me the highest decrease. So if I take a step here, it stays 6, nothing changes. If I take a step here, it stays 6, nothing changes. Backward, nothing changes. But if I take a step here, my value changes 6 to 5. So I'll take that step. Okay? I'll repeat the process. Now I'm here, and I do the same thing again. So I take step left, right, nothing changes. But if I take a step here, the value changes. So I just repeat this process. I'm doing nothing. Okay? I take the step. Again, you can understand that I'm taking the step which is decreasing my value the most, and this, and this, and this. And I found the minima. Everybody agrees with this approach? It's a simple approach. At every point that you are, you just take the step which would decrease your value the most. Yes? Well, you can say that let's assume for the time being that it's very small. Okay, I'll explain how to choose it, but for the time being, let's say that it's a very small step. And the small is relative term, I know, but in this example, we would say it's the size of one step. the one step that you are actually going up. But is it intuitive? Does it make sense? If you know nothing else and you want to find the minima of a function, you are at a point. You just go locally, you take the step which decreases the value of the function. That's the simplest thing you can do. If you go in the direction of increase of a function, that would not be very smart because you're trying to find minima. So the only intuitive option, if you know nothing else, is to go in the direction where the function value is decreasing the most, right? That's it. We have done gradient descent. We don't need anything else. So I'll give you an example. Let's say we have a function. We take the simplest example of a, let's say, convex function. And I am at this point. Okay? So which direction should I go? Toward right or toward left? Should I go in, I think it's better to use colors. Should I go in the green direction or should I go in the orange direction? Orange direction, right? Because the function is decreasing in the orange direction. So I was here. My function was here. I took a small step in orange direction. Now I'm here. What should I do now? Should I take a step in the green direction or the orange direction? Orange direction. Okay. Another step in the orange direction. I came here. And hopefully we can repeat the process. So we come here, and we come here, and we come here, and we come here. And look, we found a minima. That seems very easy. Yes? Let's make a non-linear function. Where do you want to start from? Give me a point. Okay, from top right. I start from here. I repeat the same process. I would come here, I would come here, and I would come here. That's good enough for me. Because it's a local minimum. Remember, we said we'll find a local minimum, not a global minimum. Okay? I'm sorry? Of course, it's always better to find a global minima, but it's not very easy to find the global minima. So right now, we will just make do with the local minima. Okay? So we have a technique now whereby we go in the gradient direction of a function to try to find the minima for a function. Okay? So how would we write it? So let's say you are at a point x of t. What would be x of t plus 1? So x of t plus 1 would be x of t plus the derivative of f at x of t with respect to x. Is it true exactly? Minus. Yeah, because this is increasing. We are going in the descent direction. You have to go in the negative gradient direction. So it's basically a minus here. That's it. That's an iterative scheme. You would find the value, let's say you start with any value of x of t, you find the next x of t plus 1 and the next. What would be a stopping criteria? Because this is an iterative approach, we need a stopping criteria, right? When would we stop? When would we know that most likely we have found a minima? What is the property of a minima that we have been discussing so far? Exactly. So gradient is small enough. So we would say stop if the size of is, let's say, smaller than some tolerance. Yeah. Let's say it's smaller than 0.001. Then stop. That's quite good. We have a very good scheme now to find the minimas of the function. Okay. I would pose a question to you guys now. Okay. Somebody actually already asked it. So what I'm saying is that go in the gradient direction, but with what step? Right? So no. it's 0, but the thing is if you're taking a step, let's say, I'll give you an example here. So let's say you are taking, I'm going to, let me just get another slide. It's probably better to show it clearly. So the question is, why don't we say that stop when the gradient is equal to 0? Why do we say that stop when it's small enough? Because it's an iterative scheme, right? Let's say I take this example. There is actually a possibility that you might do something like this. So let's say you come here, then you come here, then you come here, then you come here, and then you come here, and there might be some little bit of oscillation here at the bottom of this function, because you are taking some step, right? You don't know the exact step size or the best step size. You're just taking a step size in the direction of the decrease. So that's why if we are in this region close to a minima, we are fine, right? If the gradient is very small, we are fine. And another reason for this is if the gradient is very small, then x is not changing. So x of t plus 1 is equal to x of, more or less equal to x of t. So we are saying this, right? X of t plus 1 is equal to x of t minus df of x of t divided by dx. So if this is very small, then this is not changing. So you're just doing the same thing over and over again. You're not going anywhere else. It's probably better to stop. The function value is not changing a lot, so it's probably better to stop. But what we have written here is not exactly true. It's fine, but there is just one thing that we need to adjust here. And I'm just going to show you in an example here, like what is the thing that we need to adjust. So let's look at gradient descent an example, okay? So let's say I look at a function which has very high gradients, okay? So if it has very high gradients, it would look something like this, okay? I'm going to use the same color notation in order to, because it's a 1D problem, you just need either increase x or decrease x. And let's say I start here. Which direction should I go? Should I go toward the orange direction or the blue direction to find the minima? Which is the gradient direction? Negative gradient direction, sorry. Orange direction? Okay. So I take a step in orange direction. I'm here and I come here. So what happened? It doesn't look right. We started with a value of f which is this, and now we are at a value of f which is this. We were trying to get to a minima. It doesn't seem like we are going there. Any guesses as to what happened, what broke? Yeah, the step size is too big, and you cannot just take an arbitrarily large step size, right? So you have to have something here, an alpha, which tells you what step size to take. Okay? So if in this example, if I just take a small step size, then it would work. Okay? But in general, you have to have some parameter here which tells you what's the step size. And in most machine learning algorithm, you choose it to be a small value, depending on which algorithm you're using. You just choose it to be very small. But very small is not the best solution possible. There is, of course, you can find the better step. It might be more costly computationally to find the best step, but you can actually do it. So we will see some technique of how to find the best step. Okay. So it's called backtracking line search. For like bigger neural networks, you probably won't use it. You would just use constant small step size, but it's good to understand it. It's good to understand what's happening here in order to actually do it in a nicer way. So this is a condition which should be met by a good step size. So let me have a look at it. What does it say? it says that, so pk is the direction, it's a negative gradient direction. Let me just label it. Pk is the negative gradient direction, and t is the step size. Okay, and it says that take a step, or a step is only valid if the function value at the point which you go when you take the step is less than this value. Anybody wants to take a shot as to what this is? I'll give you a hint. Alpha is a parameter, and it's always less than 1. We choose it to be less than 1. So can somebody tell me if a step size t satisfies this condition, then why is it good? Or why is it a valid step size? I'll just draw it for you guys, and then maybe it would be easier for you to understand. So basically what it's saying is that let's take this example. Let's say this is xk. Okay. So this is actually a linear function. Okay. And since alpha is less than 1, it would look something like this. And what this is saying is that all these points are valid to take a step into. You can go anywhere here. You cannot go above this line. And why is it good? Why is this a good step? Why is this a good thing to do? Because, yeah. I'm sorry? Yes, it's called a condition for sufficient decrease. So there is at least a decrease in our value. We are actually decreasing a function. We are not taking a step which is too large and taking us into a region which is greater than our value at the current time. Okay, so this is a condition for sufficient decrease. Does it make sense to everyone? Okay, if alpha is 1, then it's like it's a very tough condition for decrease. So basically then it's saying is, let's say that I choose alpha equal to 1. I'm going to draw it with a blue line. Then it says that you have to go below this line. All the values of function which are below this line, which is a very difficult condition. At least it's not satisfied in this example. You would not find a valid point for it. So we say, okay, let's not be that tough. Let's keep alpha less than 1 so that you can actually find something reasonable. So that's why alpha is chosen less than 1. Okay? Does this make sense to everyone? And how do we actually use this equation, this system? So we start with a large t and we decrease it until we meet this condition. So let's say in this case I would start with, let's say, a t. Okay, I would start with a step size this. And it would bring us here, this condition is not true. So I would multiply t with beta. Beta is a constant which is less than 1. So it would bring me here. It would say, okay, take this step size. Check if this is good. No, this is not good either. So I would decrease it again. I would come here and I would decrease it again until I fall inside the valid region, and then I will take that step. So then I take that step, I come here, and now I do the backtracking at this point. Maybe I'll come here. Now I do the backtracking at this point. I'll come here, and eventually you can see that you will go to the minima slightly quicker than usual. Okay? Does it make sense to everyone? I'm sorry? Yeah, of course, of course. Exactly, yeah. Yeah. So we are actually, the thing which is changing is t. So xk is fixed, pk is fixed, alpha is fixed. You're just changing t and seeing if this is satisfied or not. If it's not satisfied, you decrease t and repeat it until t is satisfied. So this is called backtracking. It's a condition of sufficient decrease. Again, it's just to tell you that we just don't do the steepest descent blindly. There are actually some tools which we have developed to do it in a nice way. But if you want to avoid the coding, the safe bet is to just use a very small delta t. If you have a very small one, you will be fine. Okay, just a small value. What is the small value? It would depend from field to field. So let's say you would do some experiments and you would see that, oh, this is overshooting, you're not reaching a minimum. You would decrease the value, and once you have spent like maybe a few tests, you would be able to find a suitable value. But if anyone wants to implement backtracking, that's also a very valid option. This is a function. I don't think there is anything too complex about this, but this is the condition, the terminating condition. Like we said, if the gradient is too small, you stop. You are probably very close to a minima already. And the direction in which we go is the negative of the gradient, which is the steepest descent direction in which your function is changing quite a lot. P is that direction, and T is the step which satisfies that condition. It comes from this function. So this function takes in the gradient value at x, the function value at x, the direction in which you want to go, and the value of x itself, and then it tries to satisfy this for a suitable t. When it's satisfied, it returns that t and you take that step. That's it. That's a simple enough code for gradient descent. It's not very complex anymore, and it seems reasonable. Now a question, we show that for linear regression, if you had a matrix of 10,000 by 10,000, we needed a lot of operations to actually find the inverse of that matrix and find the solution through that. If you want to do it through gradient, any guesses as to how many steps we would need? So what was the gradient of linear regression? So we had A transpose AX minus Y. Okay, so this is A transpose X minus A transpose Y. So now it's a matrix multiplication rather than a matrix inverse. And matrix multiplication, if I'm not wrong, it should have something like of the order of n square, I guess, operation, right? Because you are multiplying each element of the first one with some element. Yes, so it's O n square operation, which is much smaller than a trillion. So previously we were taking 100,000 seconds. Now it would take 10 seconds to do one step, one gradient step. Okay, and then you can see that maybe it would take 100 steps or something like that. So it's much faster than what we had before. So it makes sense, make intuitive sense to actually do that. So there is actually a better direction for finding a minimum, which is called a Newton direction. I'm just going to tell you that there is a direction which is called Newton direction. I'm not going to explain it to you guys because I think it's probably slightly more complex for beginners, but you don't need to look at it. But just keep in mind, if and when you have a small system which you want to solve, you might want to look into something called Newton direction to solve it. Okay? So I would we'll take a break for 5 minutes. Let's come back at 10, and then we would see what actually is, how does the gradient descent look, and what is stochastic gradient descent as well. Okay, so I'll see you guys in 5 minutes. By the way, a question. For how many of you guys this is too simple, like you have seen this before? You have seen gradient descent and stochastic gradient descents. Because I know at least for some of you, you know this already, but how many of you have, just raise your hand so that I know that. How many of you have seen gradient descent, stochastic gradient descent, linear regression, these kind of things before? Okay, okay. Okay, that's good. So we would have some. By the way, while we are on a break, I can still take some questions. So if there is any question, raise your hand, and we can try to find a solution to that. Okay, guys. So we're going to start, and like any good teacher, I will start off with a question. Have you guys seen figures like these? Do you know what these are? Anyone? Yes, please. Okay, okay. So these are called contour plots. So let's say you have a function of two variables, f of x and y, and you want to see how the function changes as you change x and y. Of course, it's a 3D plot. For each x and y, for each x and y and xy plane, you would have a value of z, and then you wouldn't be able to see it on a paper, right? So somebody was smart and they said, okay, rather than having this 3D plot, for 2D functions we can do something interesting. We can, rather than showing the value by height, we can show it by color. Okay? So basically the color in this 2D plot represents the value of the function. Okay? But it takes it one step further. It says rather than showing the value of each point, which might be slightly tedious to see, we show the value of a function for certain values. So let's say value of all the points where the value of function is 10, all the points where value of the function is 15, all the points where value of function is 20, and so on. So the contours that you see in this figure, let's say this one, it may be for f of x and y equal to a value, let's say 100. Okay? So the line, all the points on this have a same value, which is equal to 100. Another contour that you might see, let's say this one, this might be f of xy equal to 10. For all the points on this line, the value of the function is 10. So if you want to understand what actually is doing is, you can imagine it like this. You have the surface of a function over a 2D plane, and you take a plane and cross it through that surface. It would intersect the surface at certain points, and you just show that intersection in 2D. You take that intersection and press it down on 2D and put it. And then you take another plane, let's say z equal to 1. So z equal to 1 means f of xy equal to 1. You take its intersection with the surface. It will give you all the points where the value of the function is equal to 1. You show all these points in 2D with a color. Then you take another plane, let's say z equal to 10, cross it through that surface, see its intersection with all the point of the surface, show it in a 2D plane with a different color, and so on. Okay? But that's exactly what it is. Okay? And it's used generally in 2D. You would see it in a lot of optimization textbooks to show gradient descent and stochastic gradient descent in a way which is easier for us to understand. Okay? So we start with, this is actually on this side we have gradient descent algorithm, and this is the Newton direction. So Newton direction, you can see that it takes fewer steps to reach the minima. Okay, it takes 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 9 steps in this case to reach the minima. Whereas gradient descent can actually take quite a lot. So it's 1, then 2, and then a lot of fluctuation like this. But it does eventually reach the minimum. Okay? That's just to show you, because we would probably need it in some way. Okay, next we go to a very interesting topic, which is one of the core concepts used in machine learning, So those of you who actually understood everything before that, I would like you guys to pay attention as well, because you might not have seen stochastic gradient descent up till now. Okay, so I'm just going to explain what stochastic gradient descent is and how it's used and why actually it's used. So if you remember from linear regression, the cost function that we had for certain variable theta, that was from I equal to 1 to m, h of theta of xi minus yi whole square. Okay, where I from 1 to m is my data points. Okay, now there's a problem in this cost function, and the problem in the cost function, not a problem but difficulty in terms of computation, and that is, what if m is really large? So if you remember the introduction slides, we said that okay, we can do machine learning very well because we have a lot of data. Well, we have a lot of data, but then this cost function doesn't look very easy to calculate, because you actually have to find, if you find the gradient of this cost function, you would have to find the gradient with respect to each data point, and that's just, I don't know, it looks not very easy. So I'll give you an example. For the linear regression problem, we had y, which was m's time 1 equal to a, which was m's time n is the number of bases, okay, and then you have z or theta, which is n times 1 plus some noise, okay, and then if you want to calculate the gradient for this, that was A transpose A theta minus, or z minus A transpose y. Okay. Now A transpose, so this A is m by n. So if m is huge, it's a huge matrix multiplication. Right? So what is A transpose A? A transpose A is a matrix multiplication of two matrix, which is n by m times m by n. And that's actually, it would be the product along m direction, which is huge. If it's a million or a billion, that's too much pain, right? The question is, do we actually need it? Do we actually need all the data points? So I'll give you an example. Let's say that we took the simplest example that we start with. So we had data like this. And we are fitting a line through it, right? So do we need all this data actually to calculate gradient every time? And the answer is, well, not really, but with some smart assumptions. So I'll give you the assumption and then we would see if it works or not. So the assumption is that to calculate the gradient at each time step, you don't look at the entire data, but sample a subset of that data randomly. Okay? So let's say we are doing gradient descent. We already decided that direct inversion of matrix is either not feasible or is not advised in terms of computation time. So what we need to do is we need to go in the gradient descent direction. So we just need to find the gradient and then take a step. Next we say that the gradient, we probably don't need to find it with all the data that we have in our data set. We can probably do it with a well-chosen subset of data. So what I'm saying is that we would, let's say at a given iteration 0, we would take some random points from the data, calculate the gradient with respect to that, take the step, next step, choose another random subset of data, find the gradient, take a step, and so on. Okay, so what it would change is the gradient that we were trying to find here, which was A transpose A Z minus A transpose Y, where this matrix products, for example, was n time m and m time n. So rather than using the entire m, we are using a small number which I would represent by small m. And on average, small m is much smaller than big M. So let's say you have 1 million data points, you maybe use 64, 100, 128 data points in each iteration of gradient descent. Now that's, on surface it doesn't look exactly good, because what you're trying to say is, well, let's not use the entire data and let's try to find the right solution for a subset of data, right? Because you're taking the gradient with respect to a subset of data rather than the entire data. But what makes it work is that you're choosing this subset randomly. So I'll give you an example just for illustration purpose. Let's say this one subset which we showed with blue, it's a good subset, because if you use this, you would actually probably find the line which I have drawn in red. Let's look at another subset. Let's say if you chose this as a subset. This is probably not as good. Maybe you will find a line which looks like this. Okay. Let's look at another random sampling. Maybe you will find a line which looks like this. Okay. Let's look at another random sampling. Maybe you chose something like this. You find the line maybe which looks like this. Okay. So if you do this randomly, on average you would have more lines which look like these ones. That's just an intuition of understanding it. On average, most of the steps that you would take would be close to right steps. Some of the steps might be somewhat wrong, but since you are doing it randomly, you haven't decided on one data, on a subset of data explicitly, you change this subset randomly. So on average, a large subset of your steps would be very close to the correct steps, and you would eventually reach minima. Okay, so that's something called stochastic gradient descent. In particular cases, we have certain proofs for it as well that they would converge in these cases. But in general, for a neural network, I don't think we have an explicit proof that you would actually converge to a minima. But it seems to work very well, and that's like standard practice used in machine learning algorithms. So to recap, we said that with machine learning algorithms, we have seen huge success because we have more computational power now, so we can solve bigger problems with more complexity. And then we have more data, so we can actually use more data to train. But we actually found out that there is a problem with each one of these. So we don't actually want to solve massively complex problem in a complex way. So for massively complex problem, we came up with a very simple algorithm to solve that, which just require gradient. So we come with an algorithm for which you don't need any matrix inversion. You don't need to find the best solution in a single step. You just take a step in a gradient direction. That's it. You are guaranteed, if the step is chosen well, you are guaranteed to reach a local minima. But even then we said, oh, we have a problem with data. The data which was so good for us, well, doesn't look very good now when we have to find the gradient with respect to it. So we said, okay, we will use the entire data, but we would use it in a smart way. Rather than finding the gradient with respect to entire data at each iteration, we would randomly choose a subset of the data, find the gradient with respect to that, and repeat the process until convergence. That's called stochastic gradient descent. So now we can use big data and complex model, but we can solve them in relatively non-complex, like the simplest solution that we can find for them. And we don't need to take the entire data at once and calculate the gradient. Now that seems quite reasonable. That seems reasonable in terms of computation, and in terms of complexity, we can actually do it in reasonable amount of time. So now we are all set actually to find the best solution with respect to some hypothesis function. Okay, are there any questions? Yes. How do we randomly choose? I actually haven't really looked into it. So just what I do is let's say if I have a data, I have a small simulation here. So let's say it is 100 points. I just generate random integers which represent the sample number. And then I generate it randomly in each iteration. But I think maybe if you have n samples, you just uniformly choose from any of these n's. So I think probably something like a uniform distribution over all your samples would work. Any other distribution would of course favor some data points over some other data points. So you would just uniformly sample from your data set. The likelihood of choosing any sample from your data set is, the probability of choosing any sample from the data is the same. So it should be a uniform distribution. So a question though. So if we were taking a well-chosen step in a gradient direction, negative gradient direction, we were guaranteed that our objective function would decrease. Are we guaranteed in the case of stochastic gradient descent that we would always go in the direction of decrease of the original objective? No. Okay, we are not always guaranteed to go in the direction of the decrease. You might at times go higher, but on average you would be going in the decrease direction. Does it make sense? So I'll explain it a bit. So let's say that I'm going to make a simple plot. So this is, it shows iteration, and this shows the value of j. Okay, so let's say that in the first iteration I chose the blue subset, blue as my batch, and I calculate the gradient with respect to it. So blue represents my line quite well. So basically I can expect that my cost function would probably go like this from iteration 0 to iteration 1. But now let's say in the next iteration I chose the orange batch. So the orange batch is not very representative of the data. So maybe it would look something like this. I would go in the direction of increase. But then since I'm randomly choosing, I would choose another batch which probably represents the data well, and maybe some jumps, something like that. It might be slightly wobbly, but eventually you would reach the minima. That's how generally, so you're not always guaranteed, even with a well-chosen step, that you would go in the direction of decrease of your cost function, the full cost function, because you're not actually calculating the gradient with respect to full cost function, you're calculating it with the subset of the full cost function. So technically at this point, you guys are set up with all the tools that you need to train any machine learning algorithm. So basically you are, well, quite experts now. So we will write a system here. I would write some equations, and we would try to see if we can actually find the best solution for that, or whether we can train a system or not. So by the way, the system that we have explicitly learned up till now was linear regression, which is the simplest possible. The relation in typical neural networks can be, of course, highly nonlinear. So we would try to write something which is more nonlinear and see if we can do it or not. So let's say I have certain data, x and y. So I'm not going to write index over it, but it's understood that you have different samples of it. But my hypothesis function depends on certain weights w, and it is, let's say this. It is f of w1 of x. I would explain what this means, but just give me some time. Then it's a composition with g1, which is a nonlinear function. Then it's f of w2, and then it's g2. Okay, so this is my hypothesis function. Now f of w's are linear functions. You can think of them as simple linear multiplication, where W's are the weights that we want to learn, optimally learn. Okay? And G is a function which does not have any trainable parameters, it's just a nonlinearity. Okay? So basically if we want to see how it looks, so it would look something like this. X is a vector. Okay, you multiply it with W1, which is a matrix. Okay? Then you take some nonlinear function of it, which is G1. Okay? Then you multiply the entire thing with W2, and then you take its nonlinearity, pass it through a nonlinear function. And that is your hypothesis function W, where W is W1 and W2. Okay. How do we find the right values of W1 and W2 with the tools that we have learned so far? Of course, you can write the KAUST function as well. So the KAUST function is J, which is a function of W, and it okay. So what do? I want to find the value of W1 and W2 which minimizes this KAUST function or this loss function. What I claim is that by now you guys know everything that you need to do to actually solve this system. Okay. Anybody wants to take the lead and help us find out how we can actually do it? How many of you are like really familiar with chain rule? Yeah? You are familiar with chain rule, right? You are from SEMC.
Yes.
Okay, you are familiar with chain rule. You might not know it, but you are familiar with it. Okay. So let me just make it slightly easy for you and just make a block diagram for you. So basically I have an input X. It goes through f of W1, let's say, and I call the output here, let's say Z1. Z1 is the output here. Then it goes through a nonlinear function G. Output is called A1. Then it goes through another linear function, and the output here is 2. And then it goes through here, G2, and the output is E2, and we also call it hypothesis with respect to W of X. Okay. Anybody wants to take a shot at it? And by the way, if you want to solve it, if you want to minimize this J, what do we actually need? What do we actually need to find the minima? We just need gradient. As we have aptly shown in the lecture so far, you just need to find gradient and go in the negative gradient direction. So basically what you guys need to do is find the gradient of this KAUST function with what? What are the two things that we are trying to find out? W1 and W2. Okay. For your purpose, you can assume that X is one-dimensional and W1 and W2 are just some constants that we are multiplying with X. Okay. Okay, so I seem like we probably will not get any volunteers, so I'll probably get to it myself and we'll see if we can actually do it. Okay, so we are like, I don't know, roughly 100 people here, so please don't make me do a mistake. It's on video, so if I make a mistake, correct me. Otherwise, I would look incredibly bad. So let's see. So my cost function is j of, I will write them separately so that there is no confusion, W1 and W2, and it's hypothesis function with respect to W1 and W2 of x minus y whole square. Okay, and the hypothesis function is represented like this. You have an x, it goes in f of W1, you get Z1, it goes through G1, you get A1, it goes through f of W2, and it becomes Z2, and it goes to G2 and becomes A2 or h of W1, W2 of x. Okay? So far so good. By the way, these notations Z1, A1, Z2, A2, these are just notations. You can call them anything. If you want, you can call them, I don't know, an elephant or a cat or whatever. It's just name of variables, so don't get confused by these. Okay? So the first thing, like we said, in order to optimize this energy, we would need the gradient, right? So let's try to find the gradient. So we want to find the partial derivative of j with respect to W1. Okay? So what I'm saying is, what we actually have to do is partial derivative of h of W1 and W2 x minus y whole square. Okay? First thing, let's do the simplest thing. Let's take the derivative of this function with respect to this argument. Okay? Can we do that? Somebody said yes. Raise your hand and tell us how to do it. Yes. Okay. Yep. Done. Okay. And what else? Yes. Then we need to differentiate what is inside. This is just chain rule, okay? If you have very complex looking function which is a composition of a function with a function with a function with a function, and you don't know what to do, start with the simplest thing, okay? So just imagine that this is some, let's say, I'll call it u, okay? So what does this look like? This looks like a u square, and you want to take the derivative of u square with respect to u. The derivative of this thing with what's inside. Okay, this is chain rule. So this would become 2u, and then of course, let's see u. So after this is done, whatever is inside, whatever you have defined as u, has to be differentiated with the variables that you are actually trying to find out. So if I write it formally, it would be something like this. I'm sorry. So let's say I have to find the derivative of u, which is a function of some w1 with respect to w1. I can write it like this. It would be the derivative of u square with respect to u multiplied by derivative of u with respect to w1. Okay? So this is chain rule. Make sense, or is it too confusing? Okay. So now I claim that this we don't need to look at, because y1 is an observation, it's not a function of w. You don't need to look at it. So you have to just find the derivative of the hypothesis function with respect to w1. Okay? Yes. And w1 is the difficult one, w2 is easy, but we'll do the difficult one and I'll leave the easy one for you.
So now we have this. We have to find the derivative of the hypothesis function with respect to W1.
I have dropped the subscript W1 and W2 because it's understood that hypothesis function is a function of W1 and W2.
Okay. So can I write it like this, that hypothesis function is G2 of Z2? Does everybody agree with it? So I'm just taking the definition of hypothesis function here. So what does a hypothesis function do? What is the value of hypothesis function?
It takes in Z2 and compose it with G2. Okay, find the value of G2 at Z2. Okay, I'm hoping it's clear. It's not very confusing.
Okay, and again we do the same thing. We write it as partial derivative with respect to Z2 of G2 Z2 times partial derivative of Z2 with respect to W1.
Okay, so this should be fairly easy to calculate. It's just the derivative of the function G.
Okay, so this is basically G prime of Z times.
Does it make sense?
So basically now I started from, let's say there is a cost function here, J of W1 and W2, and I'm actually, if you think about it, I found the
Partial derivative with respect to this,
found the partial derivative of J with respect to whatever was here. Now I have found the partial derivative of J with respect to whatever is here.
right? So you have to go this way back until you reach W1. That's called backpropagation.
Okay, so now I do the next bit. I'm sorry, give me 1 second. Yes, what's your question?
This is just for indexing, yeah, because I'm overloading the notation in a sense because I'm just calling it Z. But it's generally good to do it because it tells you which layer of your network you are in. Is it like the first layer, the second layer, and the third layer, or so, and so on.
So now where are we? We have to find this. We have to find
The derivative of Z2 with respect to W1.
So I'm just going to go through the next slide, and just for completion I'm just going to draw it. I'm dropping the subscripts, but of course it's obvious what I'm doing. So this is A2, Z2, A1, Z1, and I have to find now partial derivative of Z2 with respect to W1.
Okay,
So I do it like this. W1 is F2 of A1, right? That's its partial derivative of this with respect to A1 times partial derivative of A1 with respect to W1.
okay. Does it make sense, or is it confusing?
This of course should be fairly easy to calculate, because F2 of A1 is just W2 time A1. So I can calculate this thing. I just need to calculate this.
Are there any questions?
Okay. So I repeat the same procedure to find partial derivative of A with respect to W1. That would be G1 prime at Z1 times partial derivative of Z1 with respect to W1, and partial derivative of Z1 with respect to W1 is just X1. So now I have this, I put it here, it will give me this, I put it here, it will give me this, I put it here, it will give me this, and I put it here, it will give me
the gradient of j with respect to W1. That's basically backpropagation. You can repeat the same process for W2 and done. Train it. You can develop as complex a hypothesis function as you want. This basically what I wrote here, I did not tell you, but this is general representation for a neural network. It's 2 layers. But of course it can be n layers. So you have actually, without knowing, wrote the gradient descent equations for your first neural network. And that's, I think, all you need. You don't need to, you won't need it ever. You won't actually need to explicitly code these equations, but it's good to know how it works. It's good to do it at least once on paper, so that if and when you need to understand neural network, you can actually do it. So a lot of people who use neural networks use it blindly. It's like, I call it like, I don't know if you guys have it or not, but one of the old techniques of finding gold was in riverbeds. So some rivers which were in like highly enriched gold area, you just go to a riverbed and sieve it and try to find gold. So that's what a lot of machine learning people do. They just try to sieve the entire riverbed to find gold, which is slightly inconvenient. It's much better to know something about where gold is. So for that you need some knowledge of the representation as to what you are doing and how you are doing it. So again, it's just very simple application of chain rule. Okay? If it's confusing, just go to Calculus 1 book in your undergrad and see what chain rule is. Again, I am available, but for some reason you guys are shy of asking questions from me. If you ask me, I will explain it again what chain rule is. Okay? But that's it, that's all you need. You can find the gradient of as complex a cost function as you want, because neural networks are just compositions of functions. You take a function and output, compose it with another one, with another one, with another one. So you would generally need, the most complex thing that you would need from calculus is chain rule. And the functions that you need composition, that you're doing composition with, it's either a matrix multiplication or some nonlinearity. Okay, that's it. A question that I would ask you guys is, okay, we understand that we need these weights, W1 and W2. We need them in order to learn something. What are these? Why do we need these? G1 and G2. Why nonlinearity? Okay, why do we insist on putting something which has no weights? We don't learn anything from them. Why? Anybody wants to answer that? Okay, but still, if you are using W1 and W2 and W3, you are adding more and more weights. You're trying to learn more and more weights. Shouldn't that counter for it? Like, you're not saying that I'm just, let's say X was 10-dimensional. So you can say that, okay, I will get a W1 which is 1 million by 10. So now you are finding 10 million new parameters. Shouldn't it gives you something reasonable? I don't know. Right? It looks like it should, because you're learning so many new weights. Yes, that's actually true, and you are also correct. So I'll give you an example. So let's say my hypothesis function has to map a 10-dimensional function into a single-dimensional function. What it means is that X has 10 components and Y is just a value of a function. Okay, so let's say I take my example and I say that my W1 is 1 million by 10. What would my W2 have to be? Output dimension have to be 1, right? Because Y is one-dimensional, right? I cannot have more output dimension than Y because I'm representing Y with my hypothesis function. And then inner dimensions have to be 1 million
because it's a composition of the two functions. Okay, and I have removed the nonlinearities. So basically my hypothesis function is this. Hypothesis, I'm going to put a tilde on it because it's a bad hypothesis function. So it's W2 times W1 times X. And if I look at it, it's just 1 into 10. So it's just a hypothesis function where you can learn just possible 10 weights. Because it's a matrix multiplication, W2 multiplied by W1, and it would give you, it can give you nothing more than what a 1 multiplied by 10 vector can give you. So that's why you need the nonlinearities, in order to prevent this collapsing of your weight matrices. Okay? So I have some demos for gradient descent and stochastic gradient descent. We have like 10-15 minutes, so I will show them to you. Let me just this here. Okay. Somehow my MATLAB doesn't like me to change its fonts to very large. It just crashes, but it's fine. We'll just relaunch it. Any questions while MATLAB is launching? There has to be some question. It was a...
So you W1 and W2 are matrices, right?
Yes.
So once you do the chain, matrices you, I assume.
No, of course not. No. You're right. If you do the chain rule by hand, it can get quite messy for big matrices. But if you know some smart rule, you can do it in a smart way, because it would give you a tensor, a 3D tensor, if you can handle that. But generally, you don't have to do it by hand. It's just to know how it's done. Okay, like what the network is doing, actually. Again, it's not impossible. Just a little bit of patience, and you can actually do that as well. So let's see what I do here. This is, here I'm showing gradient descent, and so close it, and I'll just, the important thing is this. So let me just explain to you what is happening in this figure. First of all, we have a contour plot. So the color of the contour is showing you the value of the function. Blue means smaller value, red means higher value. So the function, typically it's minimized here. You can see that because as you go from this point outward, your function is increasing. There is a problem with this cost function in that it's not well conditioned, but you guys generally, for a second order system or for any cost function, we want the eigenvalues of the Hessian matrix not to be too different from each other. If they are too different, method like stochastic gradient descent or gradient descent have some issue. So let's see, there is a very intuitive image in my mind, but let's assume you are at the bank of a canal or a river, okay, and the river is just like this, and it goes downward, and it falls in a sea, okay, and we are trying to, the value of the function is the height
from the, let's say, center of the earth. So where is the absolute minima of this function, which looks like a river and falls in a sea? Let's say C is a point for our convenience. You have a river and it falls in a sea, and the sea is just a point. So the minima has to be the sea, because the water is going in that direction. So it means that this is at the less height. But if you're standing at the bank of the river and you're looking at the gradient direction, you want to take a step in a direction which decreases your function the most. Where would that step be? Would it be, let's say the sea is like 100 miles in that direction and the river is from that point to this point. Where will I take the step? I'll take the step like this, right? Because I'm standing at the bank of the river, and so what's happening is your function is changing a lot in this direction and it's changing very slowly in this direction. So in order to find the minima at the sea, what you would do is you would do this for eternity. You would come here and then you would come here and then you would come here. So rather than going in this direction, you are going in a combination of this direction and a very small part in that direction. That's happening because the Hessian matrix of your KAUST function has eigenvalues where one is very large and one is very small. So if it was like this, you would be going there very fast. Okay, that's just some intuition. But generally this is the best example to see this is a river. I don't know how intuitive it is to you, but for me it's like the best example that I've come up with in my life. So you just go toward the rather than going toward the sea, you're going toward the bottom towards the, I don't know, but you understand. So that's actually the problem here as well. So your function is changing very fast in this direction and very slowly in this direction. So that's why you see that in one iteration it reaches the minima in this direction, it reaches it very quickly. But here then it takes steps slowly, 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 because the gradient is small and it's a gradient descent method. And I have put a constant step size, alpha equal to, it's 0.08 somewhere up here. I haven't done this adaptive step. It comes very slowly, it takes around 5,000 iterations, but it reaches there. Okay? And it's not jumping left and right because I'm taking a really small step. Okay? Let me show you an example where gradient descent fails. So I have a step size of 0.08. Let's say I make it 0.8, and I'm not going to go for 5,000 iteration because I know it's going to fail. So small number of iterations would do. Okay. So we are in the range of 10 to power 143 and 10 to power 142. So my x is 10 to power 143 and 10 to power 142. We are somewhere, I don't know, very far away because my step is large. So it's something like this. It's a convex function. It's like our loss. It's like this. And let's say if your step size is large, you would continuously bounce out of this. So you're just going up and up and up and up and up and up and up. Somewhere too far away. So step size has to be small. Okay? And then it works. Let's see how the stochastic gradient descent looks. Again, let me just tell you what I'm doing so that nothing is like too fancy or something. So this is just gradient. I'm calculating gradient with respect to m. Again, I have applied chain rule to it. It's the derivative of mx plus b minus y whole square with respect to mx plus b minus y. So this would be 2 times mx plus b minus y. And then the derivative of mx minus y plus b minus y with respect to m, which is x. So this is the derivative with respect to m. And the derivative with respect to b is quite simple. It's just 2 times this plus multiply by 1. So very simple thing. Just notice that I have a thing gradient m old and gradient b old, and I have set them to 0, so they are not doing anything. There is a very interesting concept to solve this problem where we are like doing this on the river bank. We are doing this. We are going up and we are going down, and we are going up and we are going down. It's a concept called momentum.
So in momentum you say that rather than calculating the gradient at this point, take the average of the gradient at this point and the previous point. So I'll give you an example. So again the river example. I calculated the gradient here and it told me go there. I came here and then it says go there, right? So I have two vectors which are like this, right? So if I take the average, it would just give me this, right? So the oscillation component would kind of cancel out. This is just an intuition, but if you want to just simply improve the performance of your gradient descent, what you can do is just uncomment these and it would probably be slightly better. So that's momentum. Rather than using the value of the gradient at one point, you take the gradient at this point and the previous point, average it, or weight them in some way and take the step. Okay, so let's look at stochastic gradient descent to implement it, to run it. Okay, that's a good figure. So we will come to figure in a bit. I just want to tell you, again, very simple. Rather than finding the gradient with respect to the entire thing, inside this loop I said that generate some random indices of the data that I want to choose. And I think I'm choosing like 100 samples. We'll go up and you'll see. And then I just calculate the gradient with respect to those. So out of x and y, I just sample these points. I calculate the gradient with respect to these and I take the gradient step. Simple, nothing complex, nothing too fancy. Okay, what is this? I don't. Okay, so you can see the difference between gradient descent and stochastic gradient descent. Like we said, sometime you don't go in the direction of decrease of the function. So you can see that there are this noisy pattern. Sometimes you just, let's say you were here and then you jumped outward and then, but on average you are going towards the minima. So it's fine. You are expected some jumps, not very wanted property, but it's fine. It gives us a lot of ease in terms of processing of data. But again, it's not as clean and well directed as stochastic gradient descent. I don't know, because I, like any lazy programmer, I did not put the terminate condition. I just said that run for 5,000 iteration. Okay, but I will give you guys this code, and you can actually, of course, put the terminate and see what happens. By the way, one thing which I need to show you guys is the green represents the solution from A transpose A inverse A transpose Y. So it's the absolute global minima that I've calculated from inversion of the matrices. So you see that's right here, and we are actually quite close to it. So any questions, any comments, anything interesting that you saw today? So we have the tools now to find the best weights for any hypothesis function that we develop. Tomorrow we would start with neural networks. We would see how we can train them to find the optimum weights that we want, how we can write good representation for them which is efficient to solve. Because like you said, if the matrix is in the system, well, you can't run into some trouble, but I will try to actually do it tonight. I haven't done it yet. And hopefully we would have something good tomorrow and we can actually do it. Like the matrix form. I can do it for a 2x2 system, but I want to do it for a big system, and
show that it can actually still work. Okay. That's it from me. If there are any questions, ask them. Otherwise, if you guys want to leave, that's fine too. Okay. See